Hello students, in this video we'll discuss determinants and elementary row operations. Let's let A be an n by n matrix. Okay. What we're going to do is let's suppose, so for the first row is that suppose let E be a matrix which exchanges two rows. This is one of our elementary matrices, right? Then, determinant of A is going to be negative of the determinant of EA. Okay? In other words, if you change two rows, the effect that has on the determinant is it will change the sign of the determinant. Okay? So let's prove this. So the proof goes as follows. Proof is by induction on n. So let's check for the 2 by 2 case. So the determinant of CDAB is CB minus AD, which of course is negative AD minus BC, which is equal to negative of the determinant of ABCD. So it's true if n is equal to 2, right? Now suppose n is not 2. If n is bigger than 2, assume true for matrices of size n minus 1 by n minus 1. Okay? And then what we're going to do, so now let's take an n by n matrix. So for an n by n matrix, A, exchange two rows. So we exchange two rows, so we perform this EA operation and expand along a row which was not changed. I know since n's bigger than 2 that there's going to be at least one such row that was not changed. Now, the resulting cofactor expansion will be what? Is of matrices of size n minus 1, and the induction hypothesis imply that determinant of A is negative determinant of EA, because you can use the induction hypothesis on those n minus 1 by n minus 1 degree matrices where two rows, the original two rows have been flipped there, since I expanded along a row that was not changed. So that proves the first proposition. So if you interchange two rows in a matrix and compute the determinant of the original matrix and the determinant of the exchange matrix will be opposite sign of each other. Great, that's one property. The next property we'll prove, let's call this property number 1. Let's call property number 2. So we have interchanging two rows. We also have scaling a row. So let E lambda be the elementary matrix which scales a row. Let's say row I by lambda. Then the determinant of A is going to be lambda. Lambda times the determinant of A is going to be the determinant of E lambda applied to A. So in other words, if you scale a row by lambda, the effect it has that pulls out a factor of lambda from the determinant, okay? And so the proof is obvious. For this one has an obvious proof, right? So this is true. Expand along the scaled row. Okay? The cofactor expansion, if you scale along the scaled row, what will you have? You will have lambda times what? You'll have lambda times, let's say, A. If you're doing the ith row, I1 and then CI1A all the way down to lambda AIN CINA. And there's clearly a factor of lambda there, so this is going to be lambda times the determinant of A. That's our next row operation. Now the final row operation needs a little lemma over here. So here's a lemma. If A has two rows which are equal, then determinant of A is equal to 0, right? The proof is simple, right? If two rows are the same, let's let E exchange those rows. Then determinant of A is negative determinant of EA. But since those rows are the same, EA is the same thing as A, right? So that's negative determinant of A, right? So determinant of A is negative determinant of A. That clearly forces determinant of A to be 0, okay? And so now what's the last sort of row operation? The last row operation is if you do a multiple of one row plus another row. So 3 is that if E is an elementary operation, adding a multiple of one row to another, then determinant of A is equal to determinant of EA. In other words, if you add one row to a multiple of another row, that will not change the matrix. And we can think of a very simple reason for that. If, for example, we're computing, let's show over here, if we were doing determinant of A1, and then in the ith row you said it's AI, the ith row, plus lambda AJ down to AN, do that determinant over here, well, you would get the by the linearity of the determinant, you would see what? By cofactor expansion along this row, you would see that you would get the ordinary determinant of A, and then you would get lambda times the determinant of a matrix with two rows the same. And those will be equal to 0. So if I add a multiple of one row to another row, the addition of the row from a previous row will be identical up to a factor of lambda, which means by this lemma over here that you'll get 0. So we have 3 row operations. We have scaling, which is obvious. If you scale a row by a factor lambda, you can pull that lambda out of the determinant. If you interchange two rows, you induce a negative sign with the determinant. And finally, if you add a multiple of one row to another row, that does not affect the determinant at all. So these 3 elementary operations will be very useful for us in calculating determinants. Thank you very much.